problem solving with different functions. You'll notice you have a radioactive atom in percents. And we can see that it is decreasing or has a decay every 5 years. Now, we're not going to worry about the time in years as much as we are going to focus on the fact that this is our starting point. And then this would be one value, a second value, a third value, a fourth value, and a fifth value. All right. Now, a couple of things for us to know. Y is equal to A times B to the X. That's our exponential function equation that we were using. So I would like for you to write an equation that represents this particular graph. Now, I could give you the same data in this graph by saying, hey, you've got the XY ordered pairs. 1, 2, 3, 4, 5, where 1 is 50 and 2 is 25 and 3 is 12.5 and so forth. We're going to see our charts like this in a minute, so right now we're not going to worry about it. What we should be able to see very clearly is that between each set of data, there is a decline in half of the active radioactive atoms. So we lose another half, and we lose another half, and we lose another half. Now this is an exponential decay. And we can tell it's an exponential decay not only by the graph, but by the fact that our common ratio is 1/2. Now, our common ratio, or our rate, is the B value. So already we know that Y is equal to A times 1/2, that's our rate, raised to the X power. Now it would be helpful for us to know the A value. But how do we go about finding the A value? We find the A value by plugging in X and Y values that we know. And I'm going to pull those straight from our chart, or we could recognize them straight from our picture. I know that there's a Y value of 50. We still do not know the A value, but I know that there's a X value of 1. At this point, you notice, hey, there's only one variable. Since there's only one variable, we can simplify. 1/2 to the first power is 1/2. And we now multiply by the reciprocal to get A by itself. So times 2/1 times 2/1. 100 is equal to the value of A, and that leaves us with the equation Y is equal to 100 times 1/2 to the X value. Now, at this point, we can check every possible solution. So, our starting point is 0. That is our radioactive atoms in percent when no time has passed. So, if I plug a 0 in for X, 1/2 to the 0 is 1. 1 times 100 is 100. That matches our graph. All right, how about if I plug in a 2? 1/2 to the second power is 1/4. 1/4 times 100 is 25. So at our second value, we should be down to a Y of 25. This is our half-life decay function. Now, the only thing we need to be careful of is to remember that this is our second value, not our second year. So notice each value coincides with 5 years worth of time passing. So if we're talking about our fifth value, that would be equivalent to 25 years. Well, how do we figure out the number of years that we're talking about? What if I want to know the 400th value? Well, that's pretty easy. Notice 5 years is our first term. 5 divided by 5 is 1. 10 years is our second term. 10 divided by 5 is 2. 15 years is our third term. 15 divided by 5 is 3. So if we want to know our 400 years, what the radioactive atoms will be, we divide it by 5 so we know what term we're looking for. And so we would be looking for our 80th term. Plug 80 in for x, find the y value, and you've got your solution. All right. So when we get to the point of trying to determine the type of function, there are 3 basic types of functions that we've dealt with: linear, quadratic, and exponential. Now, linear functions have a constant rate of change. They have a constant rate of change. Exponential functions have a common ratio. Quadratic functions are the ones we haven't really talked about their rate of change. We've calculated average rate of change between any given 2 points, but haven't talked about the values specific to quadratic. We're going to see that in a little bit here. But right now, let's talk about these other 2 rates of change. Linear, constant rate of change. That means I'm adding the same value to each term. Exponential, common ratio. There is a common value getting multiplied to each term that results in the subsequent set of values. So let's look and see what's going on here. Is it linear? 16 minus something gives me 8. So minus 8. 8 minus 8. Well, that doesn't give me 4. So we know it's not linear. 16 times what gives me 8? Well, times 1/2. 8 times 1/2, that does give me 4. And 4 times 1/2, that does give me 2. So we can see very clearly that we have a common ratio, which means we're dealing with an exponential equation. Our formula for exponential equation, y is equal to a times b to the x. Now, we've seen a lot of variations of this formula. We've seen increase with interest. We've seen decrease with depreciation. We've seen a very similar formula to this when we were dealing with exponential growth with Petri dishes. We've seen a very similar formula to this when we were looking at exponential decay problems in the previous unit. So let's play with this one for a minute. Just as we saw in the warm-up, we have a b, which is our ratio. Well, we just determined our ratio. That's 1/2. So already we know that y is equal to a times the 1/2 to the x power. Well, in order to find our a value, we want to plug in an x and a y. So 16 is equal to a times 1/2 raised to the first power. All right, 1/2 to the first power, that's 1/2. And we multiply by the reciprocal to both sides of the equation to get a all by itself. So let's multiply by 2 over 1. Multiply by 2 over 1. 16 times 2 over 1 is 32 is equal to a. So now we know that y is equal to the a value that we just determined, 32, times 1/2 to the x power. And we should be able to plug any of our values from the chart up in here into this particular equation. So let's go ahead and plug in a 2. If we plug in a 2 for x, we get 1/4. 1/4 times 32 is in fact 8. So we have checked our exponential equation, and it certainly does work correctly. We can move on to the next question. All right, first determine the type of function, write out the basic formula. So let's first check for linear. 8 plus something gives me 11. Well, that's plus 3. 11 plus 3, that is 14. So far we're looking like we are linear. 14 plus 3, that's also 17. So already we know that we're dealing with a linear function. All right, since we're dealing with a linear function, we need to know what the basic formula is for a linear function. That one we dealt with a lot last year, y equals mx plus b. Our linear function has a slope or a constant rate of change, and here we notice we have a constant rate of change. We are increasing by 3. So we'll start by filling in y is equal to 3x plus b. And we're going to solve for our missing variable the same way we did in our previous problem. Plug in a value of x and y. 8 is equal to 3 times 1 plus b. Well, 3 times 1 is 3 plus b is equal to 8. Subtract 3 from both sides. 5 is equal to b. So I now know that b is equal to 5. I know that m is equal to 3. I can write an equation. Y is equal to 3x plus 5. All right. Next question. So let's check to see if this is linear. 3 plus what gives us 6? That would be plus 3. Plus 3, that does not give us 11. Can't be linear. Let's check for exponential. Do we have a common ratio? 3 times 2 gives me 6 times 2. That doesn't give me 11. So now we're at a situation we are neither linear nor exponential, so we're going to fall into quadratic. So our basic form for quadratic, y is equal to ax squared plus bx plus c. And here's where I need you to write down these new pieces of information. We are going to use a second degree of difference to calculate our a value. Now that's going to come in to be important for us to calculate our entire equation. We can calculate a where a is equal to the second degree of difference divided by 2. Well, now we need to talk about what in the world the second degree of difference is. We know the word difference means subtraction, so let's start by finding the difference. 6 and 3 gives me a difference of 3. 3 and 11 gives me a difference of 5. 11 and 18 gives me a difference of 7. That is a degree of difference. Well, it's a degree of difference from the original set of y values that we identify as the first degree of difference. In order to determine the second degree of difference, we want to find the difference of the difference. So, difference of 5 and 3 gives me 2. The difference of 5 and 7 gives me 2. Now we've got a common ratio, or what we identify as the second degree of difference. When we know the second degree of difference, that's our d sub 2 value. We can plug that into the formula. D sub 2 divided by 2 is equal to a. So a would be equal to d sub 2, which is 2, over 2, which simplifies to 1. We're doing pretty good. We know one of our ordered pairs. One of our variables. A is 1. Let's talk about the next variable we can find. The next variable we can find is going to be c. And one of the things we should have picked up from our linear understanding, y equals mx plus b, and we tend to remember, is that if x is 0, that cleans out that portion of the function and leaves us with b being equal to y. And so we recognize that b is our y-intercept. Well, the same is true for a quadratic, but you'll notice now that I have three terms, the term on the end is going to be the y-intercept when x becomes 0. Well, we can figure out an x of 0. We decrease by 1 here. And when we decrease, we need to figure out what our rate is going to be. So our difference between the terms 4 and 3 is 7. Our difference between terms 3 and 2 is 5. Our difference between terms 2 and 1 is 3. So I can see a progressive decrease of 2, which means my next difference should be a difference of 1, so that we keep the degree being the same. So 3 minus 1 gives me a value of 2. So when I plug in 0 for x, I get 2 for y. So my y-intercept is 2. That means my c value is 2. So let's start plugging in what we know. We know y is equal to 1x squared plus bx plus 2. Notice I'm missing a b, I'm missing an x, and I'm missing a y. But we can pull x's and y's from any numbers up in this chart except for the y-intercept. If we use our y-intercept values, notice that our x will be 0, which means anything multiplied to it will also be 0, which is not going to help us to identify the value of b. So we want to use any of our ordered pairs other than the y-intercept. So let's go ahead and plug in 1. 1 times 1 squared plus b times 1 plus 2 is going to be equal to the value, well, when x is 1, y is 3. So let's simplify. 1 squared is 1 times 1 is 1 plus b times 1 is just b plus 2 equals 3. Combine your like terms. 1 and 2 is 3 plus b equals 3. Subtract to get b by itself, so 0 is equal to b. Now I know the value of b, I know the value of c, I know the value of a. That gives us everything we need to write an equation. Y is equal to 1x squared, or we can just say x squared, plus 0x, well, 0 times anything disappears, plus c, which is 2. So the equation that represents this given set of data, y is equal to x squared plus 2. Well, let's check that and see if that's true. 1 squared plus 2 is 3. 2 squared, 4, plus 2 is 6. 3 squared, 9, plus 2 is 11. So sure enough, that equation works just fine for this given set of data. Hopefully that helps you understand finding equations for given sets of data.